Hello there, I have here on my breadboard a breakout board with a Texas Instruments ADS1115 16-bit analog to digital converter, and it sports 4 multiplexed inputs. You can use them single-ended or you can pair them up to have 2 differential inputs. It also sports an internal voltage reference, a programmable gain amplifier, and it communicates with my obviously Arduino Nano via the I2C bus. And yeah, obviously I have already software installed and running. It's basically an example from Adafruit. They provide a library for these things, and well, it's great. I get some values here from the voltages I feed into the inputs. 2 inputs are connected to 5-volt rail and the 2 other inputs are connected to ground. So on the breadboard, my Nano supplying everything with 5 volts, and it's a 4 serial data and a 5 serial clock pin connected to serial clock, serial data of the ADS1115 breakout board, and both lines pulled up via 2 4.7K resistors like you used to do it when you use I2C. The module has a connection to 5 volts, of course, to ground, and the analog inputs simply connected to 5 volts ground, 5 volts ground. And I get 0 and 0 on 2, and on the others I get 25,000 something, not 5 volts. Well, I guess this video will be a little bit longer than expected. Anyway, for the mailbag where I got these things, card link. Let's first have a look on what's on the breakout board, and credit where credit is due. Adafruit developed that kind of breakout board and they also sell them. So buy them please from Adafruit. I just got mine from Banggood because I didn't know about that. I just thought, oh great, analog to digital converter, and somebody asked for this video, a review of these things, and shit happens. I ordered it on Banggood, but you should order it from Adafruit on to the circuit. So the Adafruit circuit has a decoupling capacitor, 1 microfarad, okay, directly on the power input pins, and then on VDD and ground a polyfuse, okay. And the ADS1115, in our case 16-bit, has a decoupling capacitor on its power pin, 1 microfarad, probably not, and 4 resistors, so S-clock, SDA, and the alert pin are routed out to the connectors via 10K resistors, okay, and the address pin is pulled low. It's also routed to the connector via also a 10K resistor. Let's compare that to the breakout board from China. On the Chinese breakout board we have a decoupling capacitor here near our analog to digital converter. We have a 4 resistor array, 10K, and I guess these 2 are the polyfuses at the power input pin, ground and VCC, and another decoupling capacitor across ground and VCC. That one and that one are probably not 1 microfarad, but well, the datasheet of the ADS1115 says it needs only 100 nano decoupling capacitor on its power supply, and I'm not sure why we need here on 1 microfarad. So if that is a few hundred nano or all 100 nano, that should be perfectly okay. This is the code I'm currently using, and it's basically one of the examples that come with the Adafruit ADS1115 library, which also includes the Adafruit ADS1115 class, which I'm using here for the 16-bit version of that chip. The object's called ADS, and of course we need the wire library for the I2C communication. Within setup, nothing much. My serial stuff here, so I can print out something on the serial monitor. There's a lot of command stuff here, very commendable from Adafruit, what the different gains for the programmable game amplifier are, and most importantly, what the least significant bit means. In our case, and I'm using gain 2/3, it's 0.1875 millivolts per bit, or least significant bit. And the rest, ADS begin, initializes the library. We will come back to that later. And then I added that line, explicitly setting the gain for my amplifier within the ADC. Nothing much in the loop either. I have here 4 variables for the 4 channels, and they are assigned 16-bit integer. And then I have these 4 read ADC single-ended commands for my 4 analog inputs of the chip, 0, 2, 3. And obviously that function returns simply assigned 16-bit integer, not properly scaled. And the rest, I print that stuff out and there's a little delay. That's all. If we want our voltage in volts, we have to multiply the return 16-bit value here with 0.000185 volts, or 0.1875 millivolts. Let me whip up some code. That looks much better. So input 0, 4.7 odd volts, input 1, 0 volts, input 2, 4.7 something volts, and input 3 minus 0 volts. Okay. So, and my inputs are connected to 5 volt rail, ground, 5 volt rail, ground. 5 volt rail, 4.7 odd volts. Let's check that. And indeed, my multimeter says 4.7123 volts. So, seems to be okay. So, what did I change? I wrote myself a volt function that returns a float, obviously the voltage in volts, and that gets as an argument the raw 16-bit integer value from the ADC. It also gets the gain the programmable gain amplifier is operating on, and this type ADS gain T is provided within that Adafruit library. And the possible values for that are gain 2/3, gain 1, etc., up to gain 16. And depending on that, I set a multiplier float to the volts value of the least significant bit. And I use that multiplier simply to multiply the raw 16-bit value, and that gives me my value in volts. Up here I simply have redefined all these variables at floats, and I use that volt function to convert directly the values read from the ADC. And this little function here from the Adafruit library, that provides us the current gain the ADC is operating under. At this point, it might be worth to have a look into the 60-page ADS1115 datasheet. And for now, just some highlights. So supply voltage 2 volts to 5.5 volts. So that thing will work with your 3.3 volt Arduino. Programmable data rate 8 samples per second to 860 samples per second. Okay, we know that I2C interface for pin selectable addresses. We will try that. And for single-ended or two differential inputs, we will definitely try that. We are using at the moment for single-ended inputs. And we already seen that in the code. The programmable gain amplifier offers input ranges from plus minus 256 millivolts to, which we are currently using, plus minus 6.144 volts. And that's a rough diagram of what's inside our little chip. So we have here the input multiplexer, and we have the programmable gain amplifier. Note it has a positive and negative input, and it goes to a differential analog digital converter. Yeah, it has a voltage inference and reference and that I2C interface, of course, and it also has a comparator. We will try that also. And something is missing here from the MUX. There's also a line going to ground. We are currently using one of the 4 inputs single-ended, so the negative input of our pre-gain amplifier is always connected to ground. The first and most important section, absolute maximum ratings. Yeah, how not to destroy your little chip. So power supply range -3 to 7 volts. Yeah, it won't operate at -3 volts, okay. Analog input voltage, yeah, on the analog input pins, -3 volts to supply voltage plus 0.3 volts. Keep that in mind, please. Digital input voltage -3 volts to 5.5 volts. Input current continuous, which is interesting, -10 to 10 milliamps. We have to have a look into that further down the datasheet. And further down on page 15, we find that detailed picture of the input multiplexer. And you see here these diode protections on each input. Yeah, we will talk about them in a second, but while we are here, you see how that input multiplexer works, and this is the ground connection I talked about. So if you use single-ended inputs, you can use all 4 inputs and connect them here, the green line, to the positive input of your programmable gain amplifier, and the negative input of the programmable gain amplifier, that blue line, will be connected to ground. If you use that thing in differential mode, which we will do next, you can either connect the input 1 or the input 3, the other blue lines here, to the negative input of your amplifier, and then take any other input as your positive input. But now let's talk about this protection diodes. That's the 10 milliamp limit we saw in the absolute maximum ratings. Finally, we are on page 32. We find something about input protection. The important part here is the analog inputs feature protection diodes to the supply rails. Yeah, we've seen that in the multiplexer picture. However, current abilities of these diodes is limited, and they cannot take more than continuous 10 milliamps. So if you really want for input protection for higher voltages, you have to put in a serious resistance. And here again mentioned analog input voltages that exceed approximately 300 millivolts beyond the rails. That is ground minus 300 millivolts and BCC plus 300 millivolts. Okay, keep that in mind. And while we are here, unused inputs and outputs. Okay, either float unused analog inputs or tie the unused analog inputs to mid supply or VDD. Connecting unused analog inputs, which is a very common technique, to ground is possible, but may yield higher leakage currents than the previous options. So for that chip, yeah, you don't use them, let them float, the easiest. Yeah, either float no connect pins or tie the no connect pins to ground. If the alert output pin is not used, leave the pin unconnected or tie the pin to VDD using a weak pull-up resistor. So that chip is very, very tolerant about letting unused pins just float. Yeah, it's the easiest. That brings us to a probably flawed statement within the example from the Adafruit library. So it states here, yeah, the ADC input range can be changed via the following functions, blah, blah, blah. But be careful never to exceed VDD plus 0.3 volts. Yeah. And we have to add here or ground minus 0.3 volts. Yeah. But then it follows or to exceed the upper and lower limits if you adjust the input range, which is, sorry, not correct, and I will demonstrate that. I will set the gain in my software to gain 16, so our voltage range will be 0.256 volts plus minus, and yeah, that minus really can only occur, yeah, when you use differential mode. That's for differential input modes. Again, no negative voltages on the analog inputs, okay? So I'm running that now. Yeah, two of my inputs still connected to the 5 volts rail with gain 16, and yeah, nothing exploded. Let me stop the scrolling, and we get for these inputs a value of 0.2559921 volts, and it's always the same value. Yeah, normally it fluctuates a little bit, you have seen that before, and it doesn't. So that's some kind of an overflow value. It's an interesting overflow value. But anyway, our ADC should be okay, and I will prove that to you with the next version of the code, where I go back to a lower gain and we add some differential input reading. Now I'm doing in each loop 2 differential measurements between first inputs 0 and 1, and then second between inputs 2 and 3. And yeah, let me stop the auto scroll. So these are our single-ended measurements, and 4.707 minus 0.0151 should be about, yeah, 4.690. Of course, the unit doesn't do arithmetics. It really, yeah, measures the difference in voltage between the 2 inputs. And for our second pair, yeah, the ground is measured somehow a little bit lower there. I mean, breadboard, what else? Yeah, our differential is, yeah, the same like the single-ended input with 3 connected to ground. But anyway, that's a bad example. Let me take input 2 to ground. Yeah, and now we see, sorry, scrolling, and now we see differential reading from 2 to 3 is 0 volts because 2 and 3 are connected to ground. And if I connect input 3 to the 5-volt rail, we finally have, auto scroll off, a negative value to read from our AD. So anyway, again, don't put negative value, negative voltages, reference to ground, onto your analog inputs of that thing. Yeah, the negative values will appear when you do differential measuring between two inputs. And yeah, in this case, the plus input has a lower voltage than the minus input. That's it. Let's have a look at the code. It's really simple. The only change I really did was in the loop. I added 2 more variables to hold the voltage values ADC01 for the differential between the inputs 0 and 1 and ADC23 for inputs 2, 3. I added 2 more read ADC, and this time not single-ended but differential statements, to get these values. And well, the library only provides 2 statements for differential reading between the inputs 0 and 1 and between 2 and 3. We will see that in theory there's more possible here. And I print out the values. And that's all. Let's continue with the alarm feature of the chip. To demonstrate that, I have uploaded some new code into my Nano. We will have a look at that in a second. And I connected an LED to the alert pin of my breakout board. And the LED is connected with the anode to the alert pin, and the cathode of the LED goes directly to ground. There's no resistor involved because, remember, there is an onboard resistor of 10K at that alert pin. So that's the reason the LED is a little bit dim. It only gets less than half milliamp. It would need 2 milliamps to be really bright, but I think you can see it's on. Also, I connected the 0 input to the wiper of a potentiometer, and the potentiometer is between ground and 5-volt rail. Going back to the schematic I showed in the intro, I've added here that LED to the ready alert pin, and A0 is now going to the wiper of that potentiometer here between 5 volts and ground. And we are currently reading at the A0 input 0 volts. Here I'm completely here to the left. And if I turn it slowly to the right, we see the value rising quite nicely. And if I reach 3 volts, my LED should turn off. Well, that is. Right, not completely turning off, it's still blinking. Why? I will explain that in a second. Let's have a look at the code. The code I'm using is another example that comes with the Adafruit library. It's called comparator, and I just modified it a wee bit. I removed the commentary stuff we saw in the other example, so it would fit on one page. I added my explicit set gain statement here in the setup. I have my volt function further down here, so we can actually print out the measured voltage in volts. Okay. In the setup, the important thing is that statement here. Start comparator, single-ended, and then comes the number of the channel we are working on. We saw it, we work on channel 0, and then the value the comparator should act on. This is again the raw 16-bit value that our ADC expects. Yeah. So if we want the comparator to act on 3 volts, we have to divide these 3 volts by the value of the least significant bit, which is 0.1875 millivolts for a gain of 2/3, and that gives us the value of 16,000. Now that statement here causes the ADC to continuously sample. Yeah, even if we don't read anything out of it, it continuously samples and at the same time compares, comparator, the sampled value with the value we've given it here. And as soon as the measured value exceeds that limit here, the alert pin goes low and our LED goes off. Now there's a little caveat here, and this comes down in the loop. The alert will stay on, even if the actual value is decreasing again below our 3 volts, unless we read the last conversion result from the ADC, which is happening here with that statement, get last conversion results. It's only one result, but results, whatever. And that's also the reason you saw when we are going beyond 3 volts in the input, the LED basically goes out, but it still flickers, because the comparator raises the alert pin, and somewhere in the loop we read the last conversion result and we reset the comparator, but only for a very short time until it finishes the next conversion and compares the value again and says, okay, we are still over 3 volts, so I pull that pin low again. That's basically it for the comparator and alert pin and alarms and stuff that you can do with the Adafruit library. That brings us to the last feature of the Adafruit library, respectively our little analog digital converter here, and that is it can operate on 4 different addresses on the I2C bus. So you can put up to 4 of these devices on one I2C bus. And that's happening through the address pin here. And I connected the address pin now hard to my 5 volt rail. Remember, in the circuit of that breakout board, it's normally pulled down via a 10K resistor to ground. Now I pulled it up to VCC. You see I'm returned to my old code here, new feature, we can actually change the value of our 0 input. That's still working, no other hardware changes here, just pulled the address pin high. So in my schematic, the address pin, which was previously pulled down to ground by that 10K on-board resistor, is now connected to 5 volts and so pulled up high. Have a look into the code now. The code changes for that are really minimal. That was the constructor for our ADS object we used so far, and it uses as default the hexadecimal address 48, because our address pin is pulled down to ground via that 10K resistor. So this statement here is the same as that statement. But now I pulled the address pin to VDD, to our 5 volt rail, and so the address of our ADS1115 changes to hexadecimal 49. Okay, and I can pass that, and you see, I can talk to my ADC. you have two more possibilities here. You can connect the address pin to the SDA line. That will give you an address of 4A, or to the SCL line, which will give you an address of 4B. So all in all, from 48 to 4B, we can address 4 devices on the bus, which is nice. I mean, then you have 16 single-ended 16-bit ADC channels. So that's a lot. Let's have a look in the datasheet. And there on page 23, we find that I2C address selection stuff I explained already. Yeah, address pin connected to ground, VDD, SDA or SCL results in a different address of the device. And this connecting an address pin to SDA or SCL, that's a trick I didn't know before. So that's, yeah, kudos to the, Texas Instruments developers for coming up with that. And that would be it for the Adafruit library. But the ADS1115 can do a wee bit more, and the Adafruit library is not really exploring each and every feature of that. So we will now dive in a little bit further into the datasheet. And well, if you're not in modifying that library yourself and you think that's enough, you can switch off now and do something else. Remember when we first had a look at the datasheet, there was something like a programmable data rate from 8 samples per second to 860 samples per second? The Adafruit library is always using a data rate of 128 samples per second. And this table here on page 13 gives you some information how many bits are really worthwhile. That's the number in brackets, depending on your data rate and depending on your full scale range. So the gain you set. And you see that 128 samples per second is quite good compromise. You only lose 2/3 of a bit down here when you choose the highest gain. And but you can do better if you need that low full scale range. You could do better using only 64 samples per second. And if you want to be faster and you don't care about the last significant bit, you could go up in many ranges up to 475 samples per second. And if you say, okay, I don't care about the last 2 significant bits, you could go up to 860 samples per second. That brings us to the issue how these read ADC statements work from the Adafruit library. So basically they send data to the ADC and config it into, that's called a single shot mode, and 128 samples per second, and the right input or differential input, etc. Then it waits 9 milliseconds until the sample is finished, and then it reads the value from the ADC. If you have time-critical code, you can do a lot in 9 milliseconds, like query some keypad or update the display. So keep that in mind. There's room for improvement. On page 21 of the datasheet, we actually learn that our 1115 actually has 2 modes it can operate in. The single shot mode, which is used by that read ADC command from the Adafruit library, but we can also run it in continuous conversion mode, where it, with the set sample rate, it, converts from one input, okay, or from, two inputs when it's in differential mode. But that continuous conversion mode is only used by that other Adafruit library method. And that was the start comparator single-ended, okay, where we really just send the config to our ADC continuous mode and the high threshold, okay, when it should set the, or pull the alert pin down. And we get the last conversion results via the getLastConversionResults, which really just reads the value from the ADC. Talking about alerts, the ADS1115 has actually two threshold registers for the alarm. One for a high value, when you exceed that, the alarm pin is set, pulled low, and one for a low value, when your value is going below that threshold, the alert pin is also pulled low. And of course, with the Adafruit library, you can only use the high threshold. That was on page 30, by the way. Talking about the alert ready pin, and I'm on page 19. You could also use that pin to indicate when a conversion is finished. Let's say you start a conversion, or you have that thing run in continuous mode, and every time it's finished a conversion, you could, for example, connect that alert ready pin to an interrupt pin of your Arduino and read out the result of one conversion via an interrupt routine or something like that. Sorry, got one more. The Adafruit library only supports differential readings from the input pairs 0 and 1 and 2 and 3. Our 1115 also supports differential readings from the input 0 and 3 and 1 and 3. This video wouldn't be complete without having a look at some of the electrical characteristics of the ADS1115. And we start with the analog input impedance, or better, resistance. And you see it's different for common mode input and for differential input impedance. And it also depends on your gain or full scale range. And you see the higher you turn your gain, the smaller your full scale range, the lower the input impedance. So at our 2/3 gain, we have a 10 meg input impedance on common mode inputs. Sorry. And that goes down 6 meg, 3 meg, and then according to the datasheet 100 meg. I'm pretty sure that's an error in the datasheet, and it should say 100 kilo ohms. Okay, that's pretty low impedance. For differential impedance, this is much higher, and it's really the impedance between the two inputs we're talking about here. 22, 15, 4.9, 2.4, and 710 kilo ohms. So generally between two inputs, it's much higher than a single input to ground. And you can see, well, I don't believe that datasheet value here. Please also take a note on the integral nonlinearity of that ADC. So for 8 samples per second, and it gets worse higher your sample rate is, And for full scale range of 2 point something volts, it's just maximum 1 least significant bit. The offset error is typical if you use differential inputs, another least significant bit, and if you use single-ended inputs, we are typical at 3 least significant bit. So if you use that thing really single-ended, and you could throw away your last 2 bits of your value. It's there are also a gain error, which is 0.01%, which should be okay for 16-bit DA, and offset channel match, match between 2 inputs, 3 least significant bit. You should be aware this is more or less a very affordable ADC, not necessarily a high precision ADC. And I'll think I stop right now. You can read the rest yourself from the datasheet. So that's it for today. The ADS1115 turns out to be quite a versatile beast, though the Adafruit library does not explore each and every feature of it. However, as you might have guessed, I looked into the code of the Adafruit library, and it's very well written code, easy to understand, and it's a good starting point if you need to explore these other features I mentioned. And with that, I say bye.